Hello. For today's video lesson, we're going to look at the difference between a definite integral and actual bounded area. The reason this is an issue is because if you look at this particular Desmos graph, you'll see I have entered in a function and I'm finding the integral from a to b, where a is -4 and b is 4. So you can see on the graph we're going from the curve to the x-axis from here to here, and then from the x-axis to the curve from 0 to 4. What you'll notice is the actual value of the definite integral is 0, which might be kind of a strange outcome because clearly there's a whole bunch of area that's being represented by this graph, but the definite integral itself is giving us a result of 0. There's a reason for that, and it has to do with the way that integrals come about in the first place. You may or may not recall that the original goal was to find the area under a curved shape. And the way that we did it was we started by partitioning a bunch of rectangles, and the height of the rectangles are going to be calculated by the function, and the width of the rectangles are going to be a uniform change in x. So, for example, for some arbitrary value of a, f of a produces the height of this rectangle, and because the f of a value is positive, it's producing a positive height, if you will, for the rectangle. Now, change in x is always positive because it's representing a specific length, and so when we calculate the area of this one partition, this one rectangle, it's going to yield a positive number. On the other side, if I put in a b value, it's going to produce f of b, which, because the function is below the x-axis at that point, is going to be a negative number. So technically what we're getting is a negative height, if you will, of this particular rectangle. Now, try to remember the way the integrals came about was we took the sum, this is the Greek letter for sum, sigma, of the function at a bunch of different places. That represents the heights, all the heights of these rectangles, and then the delta x is the change in width. And so what we do is we allow the change in width to get infinitely small, and when we do that, that move to infinity, that limit, if you will, changes the sigma into the elongated s, and it changes the delta x into dx, and that's where the integrals come from. So when you're calculating the definite integral, you're not distinguishing whether we have positive heights or negative heights. And so the mathematics itself is going to negate all of these positive areas up here by subtracting all of these negative areas down here, and that's how we ended up with a 0 integral. So remember, the big mission is to allow the number of partitions to get infinitely large, and then you can see here we get closer to resembling the area of a curved shape. And as soon as n becomes infinity, the number of partitions, that's where you get an integral. So now the question becomes, how are we going to find an area? In other words, if the question that's being asked of us is, sorry, I lost my file here. This is bad news. If the question that's being asked is, what is the area that's being bounded by the curve as x goes from, here it is. The question is, what is the area bounded by the curve as x goes from -4 to 4? You can clearly see from the picture that there is an area, so how do we use calculus to calculate that actual area? Basically what we have to do is recognize when the function is negative in value, and then we will take the opposite of those integral values to make a positive area. This is what it would look like. For starters, we're going to take the definite integral, and in order to express it as an actual area, always positive, we're going to take the absolute value. By taking the absolute value of the function and then taking the integral, we are effectively taking all of the negative values here and making them positive, which reflects the graph upwards. So by taking the opposite of the integral of this area, we end up with this area up here, and that gives us a positive value, and hence we can figure out the total area. So in terms of the paper and pencil mathematics, we have to break up this one integral from -4 up to 4 into two separate integrals. I can see from -4 to 0 on my graph is where we have positive areas. So here from -4 to 0, I'm going to trust that the integral is going to give me a positive result and express the area under this portion of the curve. On the other side, I need to take the opposite of the integral from 0 to 4, because as x goes from 0 to 4, these are all going to be negative numbers. I will take the opposite of that negative area, and that will produce a positive result. So this is not a lesson on integrals, but as you can see here, I took the antiderivative of the polynomial, evaluate from -4 to 0, pay attention to the notation, and then from 0 to 4, I took its opposite. The rest is just number crunching, and in the end, we see 64 plus 64, or 128, is the total area. So again, that should make total sense, because here you can see this area was 64, this area was -64, but we took its opposite right here, so we have another 64 added for a grand total of 128 square units. Incidentally, you can see in the grid system, if you actually did break this up into unit by unit squares, you can count up to 128 different squares within that. So we are actually measuring real area when we do this. So one more quick example. Hopefully I can pull this up without too much stammering. Is on the same function. We're going to look at the same function, except different boundaries, and I'll show you how the whole process is supposed to look then. Of course, here comes the stammering while I try to find the file that I literally just had open. Here's one. We'll just do this. So here we have evaluate the integral from 0 to 2 of this particular function, and here we have find the total area bounded by this particular function. So I have to do in terms of getting the difference. In this one, you're just going to do all the things that we've been doing for practice. We've been practicing the fundamental theorem of calculus, which we take the antiderivative and evaluate at 2 different points. Just pay attention to the notation. The net value turns out to be 2/3. Now the way we can interpret that when we look at the graph is there's this green area here and this red area down here, and if I added the positive energy and the negative energy, there's 2/3 more space up top. So it's like the net area gained. This could be considered profits, and this could be considered losses, and this could be considered the net gain. Anyway, if this question is differently asked, it says find the total area bounded by the integral in the x-axis, then we're talking about the area here plus the area here. So in order to do that, one of the things I'd have to do is either use technology or algebra to find this x-intercept. I found the x-intercept here is 1, so as we go from 0 to 1, we're going to keep that area as positive, and as we go from 1 to 2, we're going to take the opposite of that area. So here's how I set it up. Originally, the area is going to be the integral from 0 to 2 of the integral absolute valued. And then I break up the integral from 0 to 1, keep it positive, but from 1 to 2, take its opposite. The rest is number crunching, and eventually you get a number. And it should better be bigger than 2/3, because this is now a total area situation. Turns out it's 4, which should make some sense then. If we add these two areas together, we get 4. If we take the green minus the red, we get 2/3. It's very, very much what you can do to check. Well, very much. So one last little smidge of details. You can actually enter in the absolute value of a function, and it will produce a graph then that is actually always positive. And you can just calculate the integral by going to the calculate options and doing the integral feature, and you go from 0 to 2, and it will shade in the whole area, and it will also tell you what that actual area is. If you want to evaluate an indefinite integral without knowing the total area, you can do the same thing, but not use the absolute values. Last little bit of information then. If you're wondering where the absolute values are, you can find them by using the math button. So you can find the math button right here, and then you will go to, after you hit the math button, you'll go over to number right here, the number option, and there's abs. So if you hit enter or 1, you'll pull up the absolute value, and then you could enter in the function there, and it will produce the graph for you. So anyway, yeah, that's pretty much it. I'm sorry for stammering through parts of this video, but I hope you get the gist of the information. If you need any help, just email me, and have a great day.